Swayam Prabha. Digital India. Educated India.
So we discussed that nucleophilic substitution on benzene ring is highly unlikely under the normal conditions under which we use. This reaction can, however, occur under fairly drastic conditions. So when you take bromobenzene and react it with sodium hydroxide fuse, this means you heat it up to very high temperatures. The product that you form is phenol. Similarly, when you take bromobenzene and react it with sodium amide in liquid ammonia, the product here is aniline. So this reaction can occur, but you need extreme reaction conditions for it to happen. And not only that, the reaction mechanism is also very interesting. So the proposed mechanism, the first step involves the reaction of NH2 minus with it picks up a proton and leaves behind a carbanion, and this carbanion can actually undergo a rearrangement in the following manner and produce the corresponding alkyne, which is known as benzene. Okay, so this benzene is the alkyne equivalent of benzene. So as you know, an olefin is usually referred to as an alkene, and when you have a triple bond, this is referred to as an alkyne. So similarly, this is benzene. So benzene intermediate is very interesting. And so this benzene can then further react with NH2 minus, and it produces the carbanion once again. And keep in mind that these are fairly extreme conditions under which this reaction can occur, and this eventually picks up a proton and gives you the final product. Okay, so you can convert bromobenzene to aniline using sodium amide and liquid ammonia. Okay, now if you want to understand the structure of these benzene compounds, what we need to see first is let's examine the first carbanion that is produced. So when you look at the structure of the first carbanion that is produced, I'm going to redraw the intermediate in the following manner. So basically this is the sp2 orbital, and now when this sp2 orbital sort of moves in here and kicks out bromide, the product that is formed actually has a unconventional pi bond. So you already have a pi bond over here, and this new pi bond is actually formed in the following manner. So you have this sp2 orbital and this sp2 orbital, and they actually overlap and give you the triple bond. Okay, so it is not like a conventional pi bond that is formed, but it is more likely a double bond that is formed with sp2 orbitals being overlapping with one another. Now the interesting question is that when you have substituted compounds, what would be the outcome? So when you start with let's say methoxybenzene, which is basically anisole, with the chloro in the 2 position, the product that is formed is actually the OMe, and what we are doing is we are doing NaNH2 in liquid ammonia. Okay, and the product that is formed is the following molecule, which is 1,3 substituted product. Okay, so here you start with the methoxy at 1 position and chloro at the 2 position, but you end up with methoxy at 1 position and aniline at the 3 position. So this is another piece of evidence that suggests that the benzene mechanism is actually in play. There are other pieces of evidence which are available for the formation of the benzene. Okay. Now let's look at the proposed mechanism for this reaction. So the first step, as we have already seen, would be the, so let's keep methoxy at the 1 position, chloro is at the 2 position. Okay, so the first step would be the loss of this hydrogen to NH2 minus and the formation of the carbanionic intermediate. Right? OMe Cl. Alright. Now the next step would be the loss of the chloride to give you the potentially key intermediate, which would be the benzene. Okay. Now you have two possibilities for attack. So this is the key intermediate. Now there are two possibilities. NH2 minus can attack from this side or it can attack from here. Okay. So this is going to give us possibly two products wherein you have a 1,2 attack or a 1,3 attack. That is the, with respect to the methoxy group, the attack happens either at the 2 position or at the 3 position. Okay. Now let me just draw this intermediate once again in the next page so that we can look at it more closely. Okay, so OMe is here, double bond is here, and here is the triple bond. Okay, so now let's look at both the intermediates that are formed. So NH2 minus attacks here and the negative charge moves over here. Let me just draw that out. OMe, NH2 is here and this negative charge is here. Okay, so the rest of the molecule remains intact. So in this structure, there are a couple of issues. So one is that there is going to be some possibility of steric hindrance in the attack because of the methyl group. So the 2 position may not be very favored. The second issue is that the negative charge is quite far away from the methoxy group. That is, it is meta to the methoxy group, and therefore the methoxy group does not have an inductive effect, electron withdrawing inductive effect to stabilize the negative charge. On the other hand, if the attack happens on the other carbon, so which I'm going to draw again here, OMe. So if the attack happens at the 3 position, which results in the formation of the carbanion adjacent to the methoxy group. Now we have at least solved one problem, which is of sterics. So the attack, the methoxy group is quite far away from this position. So therefore the attack doesn't necessarily have a steric hindrance. And also the electron withdrawing nature of the methoxy group by induction plays a key role in stabilizing this negative charge. So taking these two into consideration, we can help rationalize the result that we got, wherein the NH2 group is actually meta to the methoxy group in the product. Now let's consider another situation where we start with the substitution occurs in a 1,4 system. So you have, let's say, R here and you have Br over here. Now when you react it with NaNH2 in ammonia, the product that you get is actually a 1:1 mixture of these two compounds. So that is the 3 position as well as the 4 position are going to give you approximately 50% yield. 1:1 is the product ratio. So this is relatively easier for us to explain, because if you think about it, if you draw the intermediates, you have the benzene ring here, and now the attack can happen from here or from here. Okay, so NH2 minus can attack here or it can attack here. Okay, so neither of these attacks are going to be sterically hindered, so they both are quite far away. And as we discussed, the major effect is actually the inductive effect of the electron withdrawing group, and that also is quite far away for these two. So therefore, the probability of attack on this is more likely equal, and therefore you get a 50-50 mixture of the products. Now, lastly, we want to look at the reaction of one more piece of evidence for the formation of benzene. So when we start with COOH and NH2 and do a diazotization reaction on this, so when you do a NaNO2 and HCl, you can produce the diazonium salt here in triple bond N plus COO minus. Okay, so if you generate this under the appropriate conditions, then what you could do is that you could then add base OH minus, and what it does is it converts this carboxylic acid to the COO minus. Okay, so you have the formation of COO minus and N triple bond N plus. Okay, so now when you heat this up to high temperatures, what can happen is that you have a loss of carbon dioxide, C double bond O minus. Okay, so you can have a loss of CO2, and this subsequently can move here and kick out nitrogen gas. So the intermediate that is formed is the benzene. Okay, so this is a very nice way to produce benzene, and obviously the benzene is not very stable. So when you generate this benzene under these conditions, what you do is you do a cycloaddition reaction. So the cycloaddition reaction can actually happen the following manner. You can detect this in the mass spec, the cycloaddition reaction. So you can do this in the following way, and the product that you get is okay. So basically it's two benzene rings fused to one another. Okay, so the M/E ratio, that is the mass to charge ratio, is 152 for this, and you do detect this in the mass spec. So what this experiment tells you is that the benzene is likely an intermediate that is formed. You can also trap this benzene using other cycloaddition reactions, and it's routinely used in synthesis. So together, the formation of benzene is a very important sort of synthetic route that helps us substitute benzene rings, albeit under extreme conditions.